Hello students, good morning to all of you. You are most welcome in the next video lecture of LNT College online video lecture center. Okay, so today my topic is Born-Landé equation, understanding of lattice energy of ionic solids, right? So Born-Landé equation actually is a theoretical equations. So and that is used to calculate theoretically lattice energy of a ionic solids, right? So the empirical formula of Born-Landé equation is actually U is equal to minus NA m mod of z plus mod of z minus upon 4 pi epsilon 0 r0 in bracket 1 minus 1 by n. So in this equation, actually various parameters are available. So U is the lattice energy, which is measured in kilojoule per mole, right? And Na is the Avogadro's number, which has a value 6.02 into 10 to the power 23 per mole, right? So next parameter is m. So m is actually is called Madelung constant, right? So this Madelung constant uh, is actually depends on the structure of crystals or geometry of the crystals, or you can say it is obtained through the coordination numbers. And next parameter is the Z plus and Z minus. So Z plus is the charge number of the cations, right? And Z minus is charge number of anion of the ionic solids, right? So next parameter is actually epsilon 0. So epsilon 0 is nothing but we call it as permittivity of the free space. So which has a value 8.85 into 10 to the power minus 12 coulomb square per joule meter, right? So next and last parameter, that is n is equal to Born exponent. Okay, so overall this Born-Landé equation U is equal to minus NAM Z plus Z minus 4 pi epsilon 0 R0 in bracket 1 minus 1 by n. So it is a negative quantity actually, right? So this is measured in kilojoule per mole, right? How you will define lattice energy U? So what is U? First term is the U. How you can define lattice energy U? Suppose we have a ionic solids uh, that is well known, you know very well, sodium chloride, right? Sodium chloride, NaCl, solids, right? This is a ionic compound, right? So it contains actually Na plus as a cation and Cl minus as an anion, which exist in gaseous state, right? So two types of ions are actually present in the lattice, right? So this is your sodium cation and this is your chlorine. So this is your chloride ion, right? So if we wish to define lattice energy, right? So lattice energy U is defined as actually the energy which is released through the formation of 1 mole of ionic solids from its gaseous constituent ions such as cations and anions. So let us consider here sodium plus, right, in the gaseous state plus Cl minus in the gaseous state. It form NaCl in the solid state, right? So, and the lattice energy U is a negative quantity. In case of sodium chloride here, minus 786 kilojoule per mole. So, from this equation actually we can understand this sodium cation is treated as positive point charge and this chloride ion is treated as negative point charge. So suppose this is your uh, cation and this is your anion, right? And the distance between these two ions are suppose is defined as R, right? So this cation has a positive electric field and this anion has a negative electric field. It means, so there is a some sort of electrostatic interaction between cation and anion, right? So electrostatic interactions cause the formation of ionic compounds. So this once these ions come closer to each other to stabilize as a ionic compounds, the structure is stabilized and the energy is released as a energy of crystallization, right? So suppose this is cationic point charge and this is anionic point charge. Here two terms are involved actually. First term is the electrostatic attraction. So that is electrostatic attraction energy. So first term is actually U is equal to minus N A M Z plus Z minus E square, right, upon 4 pi epsilon 0 R0. So this is the first term, right? So in the previous slides here E square, right? So E is the fundamental charge or you can say elementary charge. Elementary charge which has a value 1.6 into 10 to the power minus 19 coulomb, right? So this is the final equation of the Born-Landé equations. U is equal to minus NAM Z plus mod of Z minus E square upon 4 pi epsilon 0 R in bracket 1 minus 1 by N kilojoule per mole, right? So so this is the first term. So this is coming due to the electrostatic interactions and second term U is equal to N A B upon R के power 1 N. So called B is called repulsion coefficient, right? Repulsion coefficient, right? And N is the Avogadro's numbers and here N is called Born exponent. Born exponent whose value depends on the electronic structure of the ions in a solid state, right? So by combining these two equations at room temperature, so the final equation, so that is actually U is equal to minus N A M Z plus Z minus E square upon 4 pi epsilon 0 R0 1 minus 1 by N, right? So this is the final equation of lattice um, energy, because in the Born-Landé equation, two terms are involved. First, electrostatic interaction, and second is the electrostatic repulsion, right? So here we are not going to consider polarization effect. So only two terms, that is electrostatic interaction energy and that is repulsion energy. So through the combination of these two equations, actually we can get U is equal to minus Na m Z plus Z minus E square. So from this equation, so you can easily uh, justify here is that U is the actually U is directly proportional to Z plus Z minus, right? So lattice energy is directly proportional to the product of Z plus and Z minus. It means larger the charges on ionic solids, so higher will be lattice energy, right? So, and second term is Madelung constant m, right? So directly proportional to m, Madelung constant. So greater the value of Madelung constant, so accordingly greater will be the value of lattice energy, right? So Madelung constant actually depends on the geometry, coordination number and structure of lattice, right? So of ions in the solid state, and inversely proportional to interionic distance. So R0. So R0 is nothing but interionic distance between cation and anions, right? So this is the interionic distance. Okay, suppose here is, this is your sodium and this is your chloride ion, then this is the center and this is the center. So this distance actually is called R0, right? So this is your R0 interionic distance. It means this is your positive cation and this is your negative cation. So R0, it means if the ions are more closer to each other, or distance between two ions is very low or very close to each other, then lattice energy of the ionic solids will be very high. So U increases as the product of charges on the ionic solids, and if Madelung constant is changed, then lattice energy is changed. And interionic distance, if it varies, then the lattice energy changes accordingly, right? So what is the justification of various parameters actually is that U is equal to minus N A M Z plus Z minus E square 4 pi epsilon 0 R0 1 minus 1 by N, right? So Na is the Avogadro's number. So lattice energy depends on the Avogadro's number also, because number of ions can influence the quantity of lattice energy. So here we have included Avogadro's number. Avogadro's number is nothing but number of ions, molecules or particles in a 1 mole of the ionic compounds. So in case of ionic compounds, actually the number of ions in a 1 mole of ionic compounds, so that will be multiplied in this equation. And Madelung constant, so Madelung constant varies for different lattice structure actually, and the charges, cation, anion. Suppose we have a rock salt, so that is NaCl, right? So in this solid, actually Na plus and Cl minus exist, right? Na plus gaseous, Cl minus gaseous exist. Means Z plus is equal to 1 and Z minus is equal to minus 1. So the mod of the product of charges Z plus and Z minus is equal to 1 multiply 1 is equal to 1, right? So only lattice energy is 1 times. Suppose in case of MgO, right? So in case of MgO, Mg 2 plus gaseous and oxide 2 minus gaseous. So this structure, this lattice contains Z plus is equal to 2 and Z minus is equal to minus 2. So in the second example, you can see here the product of charges. So that is Z plus and Z minus is equal to 4, right? So you can say that the lattice energy is 4 times higher in case of MgO, right? So U is the lattice energy of MgO is very high as comparison to lattice energy of NaCl, right? Because in case of MgO solid, so the product of charges is 4 times to that of the product of charges on sodium chloride. So in this way you can uh, explain easily the number of charges is high, then the lattice energy of the ionic solids will be high. Suppose we have a third example, CaF2, calcium fluoride. This calcium fluoride possesses Ca2 plus gaseous and fluorine 2F minus gaseous. Right. So the number of charges Z plus is equal to plus 2 and Z minus is equal to minus 1. So here the product of the charges Z plus and Z minus is equal to 2. So you can say that the lattice energy of this calcium fluoride is lesser than that of the MgO. So in the order U of MgO is greater than U of CaF2 is greater than U of NaCl, right? So this is the order of lattice energy in a ionic solids. So lattice energy decreases. So what is the lattice energy? Suppose we have a barium diazide N2, right? So this is barium diazide, which has barium 2 plus in the gaseous state and azide ion N2 minus in the gaseous state, right? So in case of charges production is equal to 2 multiply 1, that is 2. So the product of charges in case of barium diazide is 2, and in case of calcium fluoride the product of charges is also 2. So you are thinking that the product of charges is equivalent for both compounds, then lattice energy must be same, but it is not actually same. It also depends on the factor like size of the cation or anion, right? So what you thinking about the size of barium and calcium? So barium and calcium is the alkaline earth metal which are present in the group 2 of the periodic table. So you can say that BeMgCa, right, strontium and barium and radium, right? So calcium is, so in this group, so calcium is smaller as comparison to barium, right? So calcium 2 plus, the size of calcium 2 plus is smaller than barium 2 plus, right? So smaller the size of the cation, so it has a more lattice energy. So in case of barium diazide, barium diazide and calcium fluoride, the lattice energy of calcium fluoride is high, right? So because of the size effect. So the lattice energy depends on the size of ions, right? And second one, charges on the ions. Charges on the ions. Okay. Size in the group. If you are moving from top to bottom, in case of alkali metals, suppose this is alkali metal groups, Li, Na, K, Rb, Cs, right? So cationic radius increases as you move in this group. So the compound from these ions depends on the size of the cations and anions also, right? So in the group, once you are moving from top to bottom, lattice energy decreases, right? So lattice energy decreases, lattice energy decreases in case of these ions which forms ionic solids, right? But once you move from left to right, right? So once you move from left to right, it means the size of the ions decreases, right? From left to right in period, size of the ions decreases, right? Means lattice energy is increases. Lattice energy increases, right, in the period. But in the group, lattice energy decreases. So it all depends on the size of the ions, right? So next parameter is Madelung constant M, right? So this is your Madelung constant. Madelung constant is not specific to the ions, rather it is depends on the lattice structure, coordination number and geometry of the structure. Suppose here we have a example like NaCl, right? So NaCl is a ionic lattice in the solid state actually. So it has FCC structure, face centered cubic structure, right? And the coordination number of this rock salt, so that is Cn coordination number 6:6, right? 6:6 means H cation, that is sodium plus, is surrounded by 6 anion, and H anion, that is chloride ion, is surrounded by 6 cation. So coordination number 6:6. Okay. So in this case, Madelung constant, so that was uh, experimentally determined m is equal to 1.74. So Madelung constant is a dimensionless quantity. It has no unit actually. So this is the Madelung constant for sodium chlorides. So similarly, we have collected various datas for Madelung constant, and that can be so Madelung constant actually depends on the lattice structure. So what is the value of different types of crystal or lattice? Actually the data which I have collected is like that. In case of NaCl, the complete value is 1.74756, right? So in case of CSCl, this is the first example, and in case of CSCl, cesium chloride, so cesium chloride, it has also coordination number 6:6, and the Madelung constant m is equal to 1.76267, right? So it is larger than that of sodium chloride. So here 1.74, here 1.76 order, right? So the Madelung constant for the cesium chloride is high as comparison to the sodium chloride. And similarly, in case of calcium fluoride, so that is CaF2, in the third example, you can see in case of calcium fluoride, so it has a cubic structure and it has a coordination number of 8:4. Cn here 8:4. It means its calcium 2 plus charge is surrounded by 8 fluoride anion, and each fluoride anion is surrounded by 4 calcium cation, right? So coordination number of this calcium fluoride is 8:4 and it is a cubic structure, right? So the cubic structure geometry is different, so it has a Madelung constant m is equal to 2.51939, right? And if there is CdCl2, fourth example is the CdCl2. So that has six hexagonal structure, and it has a Madelung constant m is equal to 2.244. And similarly, this is the fifth example, Mg magnesium fluoride. So it has a tetragonal structure. So it has a tetragonal structure. So it has the Madelung constant m is equal to 2.381, right? So in this way, you can say that different geometry have different Madelung constant. Suppose one another example. So in case of ionic solids, so that is zinc sulfide. Here one example is the zinc sulfide. So it has a structure wurtzite, WURTZI, wurtzite, and hexagonal, right? So it has Madelung constant value 1.64132. And another fantastic example, that is alumina Al2O3. It has rhombohedral structure, rhombohedral, right? It has rhombohedral structure and it has the coordination number of Cn 6:4. Okay, and the Madelung constant m is equal to 4.1719. So this alumina has highest Madelung constant in the examples, right? So what you can get the inferences here is that Madelung constant m depends on the lattice structure. So if the lattice structure is actually 1D or 2D or 3D, so then the lattice energy will be different for the different lattice. So we have a various examples which contains different geometry, coordination number, and lattice structure of the ions. And here we have found that the Madelung constant depends on the geometry. So in case of alumina, here this is very high, high Madelung constant, high Madelung constant. So what you expect? U is directly proportional to Madelung constant, right? So larger the value of Madelung constant, larger the value of Madelung constant, so larger will be the lattice energy of the ionic solids. So you can say that in particular alumina possess, this alumina Al2O3 has highest lattice energy in the examples. So has very high lattice energy. So because of the high Madelung constant. So in this way, the equation, so that is Born-Landé equation depends on the Madelung constant. Okay. So Madelung constant is determined experimentally, and different structure have different value. So lattice energy will be different, right? So this is the effect of Madelung constant, and we have studies the lattice energy depends on the size of the cations or anion, and charges on the cation and anion, and Madelung constant of the ionic solids, right? And next one is called Born exponent. So that is coming from the repulsion energy, electrostatic repulsions. So here U is equal to N B upon R to the power N. So this is called, this B is called repulsion parameter, and Na is called Avogadro's number, and R is the interionic distance. R0 is the interionic distance in a SI unit, and N is the Born exponent. N is called Born exponent. Born exponent, right? And what is the value of N? Actually, it is a parameter, so which has no unit, unit free parameter, dimensionless, right? So dimensionless parameter. So the value of Born exponent depends on the electronic structure of the ions, depends on electronic structure, electronic structure of ions in solid, right? So electronic structure means electronic configuration. So different ions have different electronic configuration. So accordingly, Born exponent value can be selected. So Born exponent, this N actually ranges 5 to 12. So this Born exponent have a value in between 5 to 12, right? So which value we have to select, it depends on the electronic structure of the ionic species in the solids. So I have a data, so that is collected, and how the Born exponent changes as the lattice structure changes. So we have a data like that. electronic, suppose we have a data, electronic configuration of ions, electronic configuration of ions, right, in an ionic compound, in an ionic compound, right, and example of ions, ions, and this is the end value, right. So suppose we have a electronic configuration like noble gas, right. So suppose ions H plus and Li plus. Here principal quantum number, one another column is that principal quantum number, right. So principal quantum number correspond to the outermost shell. So in case of H plus and Li plus is 1, right. And if the ions have electronic configuration like neon, suppose we have F minus example, F minus O2 minus Na plus and Mg2 plus, right, Mg2 plus. So in case of principal quantum number here 2, right. So all these ionic species have electronic configuration similar to this neon, right. So for this Born exponent is actually 5. If the principal quantum number is 1 and the electronic configuration of ions look like helium, then it has a Born exponent 5. But in case of neon, which have a electronic configuration for the ions similar to the neon, so it has a principal quantum number 2 and the Born exponent 7, right. And third one, if it has a electronic configuration like argon, it means the ions Cl minus S2 minus K plus and Ca2 plus Cu plus, right. In case of these ions, the Born exponent are expected to increase, that is 9. And in case of krypton like electronic configuration, it means, so in case of this, so there is 3 principal quantum number, and in case of krypton like electronic configuration, so it has principal quantum number that is 4, and the examples include Br minus, Rb plus and Sr2 plus, right, and silver plus. In case of these ions, Born exponent approaches to 10, right. And in case of xenon electronic configuration, so the coordination number actually includes 5. Sorry, this is the principal quantum number which approaches to 5, and the ions I minus and Cs plus and barium 2 plus Au plus. So in this case, the Born exponent is very high, that is 12. So suppose we have a ionic compounds like LiF and another one is LII, right? The Born exponent for this compound is high and Born exponent for this compound is low, and low. In case of this, N high, right? So since Born exponent is inversely proportional to the lattice energy, so larger the value of Born exponent, lower will be lattice energy. So LIF possesses highest lattice energy, HIGH, highest lattice energy, while lithium iodide possesses low lattice energy. Right? So Born exponent, so that is the average value. So N average, so which is the value actually, the Born exponent correspond to cation. So and the Born exponent correspond to anion. If you add these two value and divide by 2, then we can get the average Born exponent for the cation. So suppose we have a example like MgO. For MgO, N is equal to 7. Suppose you have a example that is magnesium oxide, right? So in case of magnesium oxide, Born exponent is 7, right? Because it has electronic configuration like neon, right? And the Born exponent correspond to this neon, that is oxide and magnesium 2 plus. Both ions, cation and anion, exist in this structure. So here average Born exponent N is equal to 7 plus 7 upon 2 is equal to 7, right? So for MgO, Born exponent is 7. And in case of lithium chloride, suppose we have example that is lithium chloride, right? So lithium plus exists in the electronic configuration of helium. So it has Born exponent 5. So N average 5 plus, and chloride ion exists in the electronic configuration like argon. So this chloride has the value 9 and divide upon 2. So in this case also there is 7. So for the MgO, Born exponent is 7, and in case of lithium chloride there is also a Born exponent 7, right? So this is the way by which we can determine Born exponent, so that is average quantity from the these datas, and we can calculate lattice enthalpy. So, in a conclusion, lattice enthalpy actually uh, depends on the various parameters. We have well aware about that in this lecture. So, what inferences is drawn from the lattice energy? So, lattice energy, that is U, right? So, it has a definition like that. So, the energy released when 1 mole of ionic solid formed through the combination of its gaseous cation and anion. So, this is the evolvement of energy. So, energy is evolved. So, always U is a negative quantity when the ionic solid is formed. It means lattice structure is going to be stabilized. So, it has negative energy. So, in this way, and in the second way, we can break the lattice. Suppose we have sodium chloride in a solid state, right? So, it can be broken down to its constituent gaseous cation and anion, right? So, in this case, the lattice energy is positive, right? So, in case this is positive, but reverse when Na plus gaseous plus Cl minus gaseous once form NaCl solid. So, in case of this reaction, when lattice structure is formed, when ionic solid is formed, then the lattice energy is negative, and when crystal is broken down, when ionic solid is broken down into its constituent cations and anions in the gaseous state, then the external energy is required. So, lattice energy is positive, right? So, in case of lattice energy for the alkali metals, suppose we have LiF, NaF, Kf, Rbf, and CSF. Here anion is fixed and cation is buried in case of alkali metal cations. So, lithium fluoride, and this is the cesium fluoride. So, what you are expecting, the order of lattice energy. So, in case of lithium fluoride, the size of the Li plus and Fi minus is low or smaller compared to the other respective cations and anions in the group. So, this lithium fluoride possesses highest lattice energy, while cesium fluoride possesses lowest lattice energy, right? So, in this way, order of the lattice energy, like lithium fluoride has greater than the sodium fluoride, has greater than the potassium fluoride, has greater than the rubidium fluoride, and greater than cesium fluoride. So, lattice energy decreases in the group. Lattice energy decreases in group because of the size effect. Since charges on each ions are equivalent, only here the factor is effective, that is size. So from moving top to bottom, the size of the ions actually increases and lattice energy decreases. Suppose in the next example, LiF, LiCl, LiBr, Li iodine. So here anion is buried and cation is fixed. So this is the lithium fluoride and this is lithium iodide. Again, lithium plus has fixed charge, and that is the charges on the fluoride. So it contains Li plus and F minus. Similarly, Cl minus, similarly Br minus, and similarly I minus, right? So the size of the anions in this halogen family increases, size increases in this group. So if the size is increased in the group, the lattice energy is decreases. So the highest lattice energy in this group possesses lithium fluoride. So it has high lattice energy, right? Lattice energy, and it has lowest lattice energy. Lattice energy, right? So this is the explanation of lattice energy, which actually depends on the size of the cation and anion. So we have also collected data for alkali metal halides. Suppose we have an example for the lattice energy halides. LiCl, NaCl, KCl, and RbCl, and TSCl. So it has -845, it has -770, and it has -703 and -674 and -644. So from these data in kilojoule per mole, so this is your kilojoule per mole. For the first group, alkali metal lithium halides like lithium chloride, sodium chloride, potassium chloride, rubidium chloride, and cesium chloride. So the data are like that. In case of lithium chloride, it has very high lattice enthalpy, that is -845. And in case of cesium chlorides, so it has only 644 kilojoule per mole. So here is the size effect of the cations, right? So in case of lithium chloride, is small and highly charged Li plus Cl minus, and in case of cesium chloride, it has bigger cesium plus and chloride ion. So the lowest lattice energy for the cesium chloride in this group and highest lattice energy for the lithium chloride for this group. So lattice energy decreases in this group. From this data you can explain. So these are the various parameters and examples and data which confirms the lattice energy and its concept, right? So what are the uh, factors that I have previously explained very well for the lattice energy? And the lattice energy, this U, that is lattice energy U, lattice energy, right? So this lattice energy U, actually it has a capacity to explain about melting point, right? Boiling point, solubility, materials design, right? So lattice energy used to explain about the melting point, boiling point, solubility, and materials design behavior of ionic compounds. So lattice energy, if lattice energy U is very high, it means melting point and boiling point is directly proportional to lattice energy. So lattice energy is very high, then melting point and boiling point of the ionic solid will be very, very high. So if lattice energy is very, very high, it means actually there is high degree of electrostatic interactions between the cation and anions. So more stable the crystal structure and more ordered structure and more crystalline structure have more boiling and melting points. So greater the value of lattice energy, higher will be melting and boiling point of the ionic solids, right? And solubility, U determines the solubility behavior of the ionic compounds. So suppose we have a ionic compound. So if this ionic compound has very, very high lattice energy, then what you are expecting? So high lattice energy means the electrostatic interactions, electrostatic force between these two ions are very, very strong, and the lattice structure is more stabilized, and the forces that binds the ions are very strong. So it cannot be easily separated from the lattice structure. So the solubility in water or any other solvent decreases. So high lattice enthalpy or lattice energy U, if this is higher, then solubility will be low. Low solubility. Solubility low. So larger or greater lattice energy means that ionic solid is less soluble in the solvent. So larger lattice energy means the ionic compound is not susceptible to dissolved easily, right? So if the lattice energy is smaller or it has a small value, then the forces between the ions are weak and it can be easily broken down by the solvent. So it will be easily solubilized. So lower lattice energy means ionic compounds, ionic compounds, ionic compound undergo rapid dissolution. Rapid dissolution. It means lower the value of lattice energy of ionic compound, the solubility will be very, very high in the particular solvent. And the one thing is important here is the dielectric constant of the solvent. So epsilon, so that is dielectric constant for water, that is 82, right? So if the dielectric constant is very, very high, then the electrostatic force, so that binds the cation anion, will be weakened down. So will be easily broken down, since electrostatic force Fe 1 by 4 pi epsilon 0 Q1 Q2 upon R square होता है, right? So epsilon, so this value is very high. This is inversely proportional to electrostatic force. So electrostatic force is inversely proportional to the dielectric constant. Dielectric constant. So larger the value of dielectric constant of the solvent, so lower will be the force between the ions in the of the ionic compounds. So it will be easily dissolved in the solvent. So in this way, lattice energy is very useful parameters in the chemistry, uh, especially in the solid state chemistry. So which gives us idea about the melting point of the ionic compounds, boiling point of the ionic compounds, solubility behavior, and finally we can design the ionic compounds, so depending on the solubility or insolubility. So sometimes calcium carbonate, suppose we have calcium carbonate, that is Sangmarmar, so which is limestone. So that calcium carbonate is also ionic. So because of presence of calcium 2 plus and carbonate 2 minus charge. But this ionic compound is not soluble in water. So because it has 4 times high lattice energy as comparison to NaCl, right? So NaCl is easily dissolved in the water because of low lattice energy, while calcium carbonate does not dissolve in the water because of 4 times high lattice energy of this calcium carbonate. So because here charges Z plus and Z minus, that is product will be 4. In case of product will be 1, right? So for the sodium chloride lattice energy and for the calcium carbonate lattice energy is very different. So that is why calcium carbonate is insoluble in water while sodium chloride is soluble in water. So because of the lattice energy. And another parameters, so that is actually help to dissolve the ionic compounds, so that is hydration energy. So hydration energy, right? So hydration energy is nothing but it is also the energy released or evolved when a particular ionic solids is dissolved in the water. So that is in case of sodium NaCl solid. So if it is dissolved in H2O, right? So it has two types of ions, so that is Na plus aqueous and Cl minus aqueous. So the number of H2O molecule that surrounds the cation will determine the energy of hydration. Similarly, the number of H2O molecule so that surrounds the anion is actually determines the hydration energy. So hydration energy is delta H. Hydration is directly proportional to the number of water or water molecule that associated to the ions surroundings the ion. Water molecule which surrounds the ion. So larger the number of water molecule that surrounds the cation, so it has a more hydration. So more water molecule is binded through these ions, right? So hydration energy will be very high. So the solubility is actually depends on the hydration energy and lattice energy. If delta H hydration is greater than delta H lattice, so lattice, right? Or you can say H delta H hydration is greater than delta U lattice. So if this satisfied, then the ionic compounds will be soluble in the water. So any ionic compounds, so that is soluble in the water, must possess high hydration energy, right? So rather than the lattice energy. So you can say that the calcium carbonate has large lattice energy compared to the hydration energy. So it is not easily soluble in the water. So in this way, hydration energy depends on the size of the individual ions. So that is delta H hydration is inversely proportional to 1 upon R, right? So R, it may be either size of the cation or anion. So R is the size of individual ions, right? So larger the size of the cation or anion, so lower will be the hydration energy, and if lower is the hydration energy, it means it is not going to be solubilized in the water. So for solubility, the size of the cations should be low, or smaller compounds, smaller ions, so that forms ionic compounds are actually more soluble than that of, suppose, LiCl and CsCl, right? So this is your lithium chloride and this is your cesium chloride. So this cesium chloride is actually formed from the bigger size of the cation, and this is formed through the smaller cation. So it has more hydration of ion. So lithium plus, so this lithium plus surrounds large number of water molecules, right? So this lithium plus, because of the small size, so it has sheath of hydration cell. So that is sheath of hydration cell. So that is very high. But in case of cesium plus, the sheath of the sheath of hydration cell, right, is low. It means cesium can accommodate lower number of water molecule, while lithium can accommodate uh, large number of water molecules. So the compound formed through this lithium cation, so lithium Cl, and the compound formed through this cesium cation, CsCl. So this is less soluble, because a small number of water molecule is attached through cesium cation, and this is more soluble, more soluble because more number of water molecule that surrounds the lithium cation. Okay, so this is the final understanding of the lattice energy, hydration energy. So that actually will be helpful to understanding the behavior of ionic solids, ionic compounds in reference to, that is, melting point, boiling point, and solubility, as well as the compound designing and compound engineering. So this is the way by which we can explain here. So this is the Born-Landé equation, that is most important equation, actually help to understand the chemistry of the ionic solids. Okay, so thank you students for listening this topic. So that will be helpful to understand the first semester as well as third semester and fourth semester, or any semester students at a undergraduate level or postgraduate level, so which will be very useful. So okay, thank you. Again I will meet you in the next video tomorrow. Okay.